Let's start the last section in Chapter 3. We're talking about rational functions. We want to study properties of rational functions, and we want to be able to sketch the graph of a rational function. A rational function is just the ratio of two polynomial functions. We've been studying polynomials already in Chapter 3, and we studied linear functions, linear polynomials, in Chapter 2. So if we just take two polynomials and make a fraction, then that new function is called a rational function. And you can see some examples here. There are two basic rational functions that we want to talk about first. The first one is y equals 1 over x. And so let's start with a table and a graph for y equals 1 over x. If we plug each of the x values into the function, then we'll get points that we can plot. You might want to take a moment and pause the video and try to complete the table and the graph on your own. 1 divided by -4 is -1/4. 1 divided by -2 is -1/2. 1 divided by -1 simplifies to -1. The next input might be tricky because we have to deal with the complex fraction. Remember, dividing by -1/2 is the same as multiplying by its reciprocal. And so the answer is just -2. Similarly, if x is -1/4, y is -4. If we put 0 in for x, division by 0 is undefined. 1 divided by 0 is not a number. 0 is not in the domain of the function. We can go on now and finish the table. 1 over 1/4 is 4, and then 2, and then 1, and then 1/2, and then 1/4. Okay, so we can go ahead and plot these points and connect them up with a smooth curve to see the graph. Notice that the two pieces of the graph, the piece over here in the bottom left and the piece over here in the top right, don't connect together. There's a gap in between them because there is no point at x equals 0, because when x equals 0, the function is undefined. So what does the graph do as it gets close to 0? Well, if we think about it, it shoots up on the right side and it shoots down on the left side. How do we know this? Well, we could plot more points. We could think, what if x is 1/10? That's really close to 0, just on the right of 0. If x is 1/10, then y is 10. So it's way up high on the graph. And if you got even closer, suppose you had x is 1 over 100 or 0.01. What is y then? If x is 1 over 100, then y is 100. And so the graph shoots up toward infinity on just to the right of 0, and similarly shoots down just to the left of 0. We'll say that again in just a minute. That's going to lead us right into a vertical asymptote. Okay, before we get back to that, let's go ahead and finish the graph. Let's connect the points out here to the right. And notice as we go past 4, the graph continues to level off and get closer and closer to the x-axis. How do we know that? Well, we could plug in more values for x. For example, what if x is 10? Then what is y? Y is 1 over 10 or 0.1. So that's even closer to 0. What if x is 100 or 1,000 or 1,000,000? Then y is a positive number closer and closer to 0, but still greater than 0. So we never actually get to the x-axis. We never actually get y equals 0. We just get closer and closer. This is different than a polynomial function. If you remember those graphs in the previous sections, they always shot up or down at the left and the right ends of the graph. This graph, a rational function, can level off as 1 over x does. Levels off toward y equals 0. And it does the same thing for similar reasons at the left end of the graph. Okay, so let's talk about this behavior one more time. So what did we say here? First we said as x gets close to 0, y shoots off to positive infinity on the right side and negative infinity on the left side. We could also write that a little more succinctly. We could use some symbols that you might remember from a previous section. We could say as x approaches 0, y approaches plus or minus infinity. And then let's write it one more time. Let's write as x approaches 0. You could also write this as the absolute value of y, or you could even call it f of x. Right? Y is the same as f of x. You could say the absolute value is the magnitude of the number. The magnitude of the number gets really large, either positive or negative. Well, what we're describing here is exactly the definition of a vertical asymptote. And so let's come over on the graph right beside the y-axis. Let's label a vertical asymptote at x equals 0. At x equals 0. And so what we're saying is that whenever you have behavior like what we just described, that's the condition for a vertical asymptote. Here's our definition. As x approaches some constant value a, f of x approaches plus or minus infinity. In this case, the value of a is 0. Okay. And then there's another observation that we want to make. Which is to say, as x gets large, as x goes off to positive or negative infinity, as x goes to positive or negative infinity, what does y do? Out at the right end, x goes to infinity, and y keeps getting closer and closer to 0. And it's the same thing at the left end of the graph. As x goes to negative infinity, y gets closer and closer to 0. So we could rewrite that as x approaches positive or negative infinity, y approaches 0. Or we could write as the magnitude of x approaches infinity, right? Then that says the same thing, right? That says that we're either at the left or the right end of the graph. X is approaching positive or negative infinity, so the absolute value of X is approaching infinity. Those are equivalent. We can say that the function, we can still call it y, or we could get a little more formal and use the function notation. We could say f of x approaches 0. Well, that's exactly the condition for a horizontal asymptote. So we have a horizontal asymptote at y equals 0. And I believe I have that definition down here as well. Y equals k is a horizontal asymptote if you have this behavior. As x approaches positive or negative infinity, y approaches some fixed value. In this case, y is approaching 0. So the value of k is 0. And so the horizontal line, the horizontal asymptote, would be y equals 0. And that's what we have labeled here. Okay, so that's the most important thing that I wanted to say about this graph. There are a couple other things I'd like to say as well. I'd like to remind you about the domain and the range. The domain and the range are the same for this graph. Do you see what it is? If we work on the domain, we look at all of the x values from left to right. Every x value, every real number is in the domain except for 1, except for 0. So the domain is all real numbers except 0. We can write that in interval notation, just like this. All real numbers except for 0. And then you can see that the range is the same. That's all the y values. If we look from the bottom of the graph down here at negative infinity, all the y values are accounted for, are included in the graph. All real numbers are included as y values in the graph except for 0. Y is never equal to 0. Okay, so we have the domain and the range. We have the asymptotes. Notice there is no x-intercept and there is no y-intercept. This graph never crosses either axis. Discontinuities. The discontinuity is the jump or the gap at x equals 0. And the last thing you could say is the symmetry. We studied symmetry a little bit in chapter 2. So if you remember even and odd functions, this function is odd. It has a rotational symmetry of 180 degrees about the origin.